Welcome back to the NET series, and we'll continue with our chapter number 5, which was of circular motion. And this is the part 3 and the final part of circular motion. So let's start by listing some of the quantities with their relations to each other. Specifically, we'll list the translational and rotational quantities, and we'll see how we can relate those two quantities. So here is a list of quantities and the translation version of them and the rotational version of them. And here we have the relation between the rotational and the translational version of these quantities. So let's start with the first one, which is displacement. And displacement, the translation version of it is just a vector d, which defines displacement. In rotational motion, the displacement is measured in angle theta, right? So this could be measured in radians or degrees, but it's measured in radians typically, right? And so we can relate these two, d and theta, using the arc length, which is s is equal to r times theta. So here s behaves as the translation d. Moving on, we have velocity, and velocity vector is simply the displacement vector over time. So the rotational analog of the velocity vector is the angular velocity, which is simply how the rotational displacement changes per unit time, right? So this is the time taken to perform this rotation. So if I draw something like that over here, so let's say we have a circle, and initially our vector pointed in this direction, and now it's in this direction. So the displacement is this angle theta, and the time it took for this vector to move from this point to this point is delta t, right? So you can relate the two using this relation, which says that the translational or the tangential velocity is equal to r times angular velocity. Then we have acceleration, and the translational acceleration is simply defined as the change in the translational velocity, or the tangential velocity for that matter, divided by the time it takes for this change in velocity to happen. And now the rotational analog of translational velocity is the angular velocity, which is represented with this alpha, and that is simply the change in angular velocity divided by the time it takes to change this angular velocity from one value to another value. And you can relate these translational and the angular velocity using this relation, which is the translational velocity is equal to r times the angular velocity. Remember, this r is just the position vector from the center of the circle, right? And if I put the value of angular velocity, then you can get to the radial radial acceleration as r omega squared, right? So here are two expressions which basically relate the translational velocity to the angular velocity, and similarly the radial acceleration. Sorry, I said velocity, what I meant was acceleration, right? So the translational acceleration to the angular acceleration, and radial acceleration to the angular acceleration. Right, so moving on, we have mass. Now, mass is basically in translational motion, what we have is mass. So mass defines that stuff of matter. But in rotational motion, the analog of mass is used, which is the moment of inertia, which is represented with this I. And it's equal to mr squared. So the moment of inertia is actually defined with respect to some rotation axis. So for example, if I were to draw something like this, a circle, let's say, and it's rotating about its center, right? So it's rotating about this axis. So the moment of inertia of this disk would be defined with respect to this rotation axis in this case. So you could have an object rotating about different axes. So maybe you could have something like this, and this is rotating about this axis. Then you would have some other moment of inertia for this object, right? So that means that the moment of inertia is actually defined with respect to a specific rotation axis. And you can relate the moment of inertia with mass by simply summing over all the mr squares, right? Where m is the mass and r is the position vector. Next, we have force and force or torque. So in the translational motion, what we have is a force, and it is defined as the mass times the acceleration of an object. So if I push something, if I apply a force, that is equal to producing an acceleration. Now, in rotational motion, we don't really have something as a force, but instead, what we have is what is called a torque. And this torque is responsible for producing an angular acceleration. So, so a body is rotating and you apply some net torque to it, it would produce an acceleration in the rotational motion. Now, there is no relation for relating the torque to F as such, except for the fact that it's just R cross F. So it's the vector product of these two vectors. Next, we have kinetic energy. Now, kinetic energy in translational motion, kinetic energy is, as you all know, is the energy that a moving object will possess, and so it's defined for a translational motion as half times the mass of the object times the translational velocity squared. And in the rotational motion, we have the analog of mass, which is the moment of inertia, and we have the analog of the velocity, which is angular velocity. So we have half I omega squared. Moving on, we have momentum, and a translational momentum is defined as the product of mass times the velocity of the object. Whereas the rotational momentum, also called the angular momentum, it is defined as the product of the analog of mass, which is the moment of inertia, times the analog of the velocity, which is angular velocity. And you can relate the two with the vector product of the position vector r and the linear momentum p. So it's r cross p gives you the angular momentum of the object. Now, you must note over here that the angular momentum, it is dependent on the axis of rotation that you choose, right? Next, you have power, and power is defined as the product of force times velocity. So power is basically how quickly I can cause an acceleration. And in the rotational motion, the analog of force is used, which is torque, and the analog of velocity in rotational motion is angular velocity, right? So power is defined in rotational motion as torque times the angular velocity. Moving on, we have work, and we have in the translational motion, the work is defined simply as the dot product of force vector and the displacement vector. And again, in the rotational motion, think about the analog of force, which is torque, and the analog of displacement, which is the angular displacement, which was theta. So it is the dot product of the torque and the angular displacement. Moving on, we have impulse, and impulse for a translational motion was defined as the product of force multiplied by the duration for how long this force was applied on the system. So that's impulse in the translational motion. Now, similarly, in the rotational motion, the analog of force, which is torque, is used multiplied by the duration of time for which the torque would be applied on the system. And the equilibrium condition in the translational motion is defined as sum of all of the forces acting on the system is set to 0, right? While in the rotational motion, we have sum of all of the net torque acting on the system should vanish, right? So now if you think about this, it's pretty or quite easy to remember all of these expressions. If you know the expressions for translational quantities, then it's very easy to remember rotational quantities expressions if you know the analogs of, for example, the analog of mass is just the moment of inertia, the analog of force is just torque, and so on, right? So all you have to do is remember the expressions for the translational quantities, and you have to know what are the analogs of those quantities in rotational frame. Now let's move on to the next topic, which is of artificial satellites. So what is an artificial satellite? Well, first of all, what is an actual satellite? You know that the Earth, planet Earth, has something that revolves around this planet Earth, and we know that's moon, right? So anything that is orbiting the Earth, this is the Earth, let's write it down. So anything that orbits the Earth, it's basically naturally orbiting the Earth without no human made this moon, right? It was by nature, and it's naturally orbiting the Earth. So this thing, moon, is defined as an actual satellite of the Earth. However, it is possible to make artificial satellites and send them into the orbit of the Earth as well. So whenever we have any object that is going to revolve or orbit the Earth, or any planet for that matter, that is termed as a satellite. And as discussed just now, moon is a natural satellite to the Earth, right? So it's a natural satellite to the Earth. Note that the orbital angular velocity and the spin angular velocity for the moon, it's the same, right? So these two velocities are equal to each other. So what do we mean by orbital and spin angular velocity? Think about this diagram. So moon is orbiting the Earth, right? So it would orbit the Earth with some angular velocity. That's obvious, right? But the moon itself, it's also spinning about its axis of rotation. So let's suppose, for example, this is the axis of rotation. So it's performing a spin motion about this axis of rotation. So it's spinning. You can imagine a ball, and if you spin that ball about an axis, so it's something like that. So it happens so that the orbital velocity and the spin velocity, let's call omega s as the spin angular velocity and omega o as the orbital angular velocity. For the moon, it's the same. So we have omega s is equal to omega o. Right. Now, if you have a man-made rocket or a spaceship that orbits the Earth, right? Now, that object, rocket or spaceship, is termed as an artificial satellite. And these artificial satellites, they revolve around the Earth, or they orbit the planet due to the effects of gravity, or you can say due to the force of gravity of the Earth, right? Remember, from the previous lecture, we can compute the critical velocity of the orbit. So for an artificial satellite, the critical velocity, it's given by Vc is equal to square root gr. And if I put the radius of the Earth, if I want to send my artificial satellite in the orbit of Earth, then we would have the radius of the Earth and the acceleration of gravity due to the Earth. And then this would give you something round about 7.9 kilometers per second. So what does this mean? This means that if you want your artificial satellite to be in the orbit of the Earth, right, in the stable Earth's orbit, then it has to be moving with a translational velocity of at least 7.9 kilometers per second. So it has to maintain this velocity to orbit the Earth. So any velocity that would be lower or higher would pull it out of the orbit. So the time that it takes to complete an orbit for the artificial satellite, which is actually known as a period of that satellite, that is roundabout to 5060 seconds. And if I convert this into minutes, it would be 84 minutes. Note that this would be a geostationary orbit. And geostationary orbits, they're sometimes also called a parking orbit, right? So moving forward, let's discuss the universal law of gravitation. This law of gravitation was given to us or passed down to us by Sir Isaac Newton. Now we have this law of gravitation, but Newton himself did not know what is the source of gravity, because it appears though, as we have two masses. Let's consider this is mass m and this is some other mass small m. Now because this is a larger mass, so this small m would be more attracted towards this larger mass, while this would be also attracted towards the smaller mass, but with a less force, right? So we'll see how this works when we write down the universal law, but this is what happens. However, there is nothing in between these two masses that's pulling them together, right? So it's as though there is some action at a distance at play in this case. However, that cannot be true. So Newton did not know why this happens. So at the end of his book in Principia, he wrote down that he does not know, and that's left the interpretation of how this works is left as an exercise to the reader, right? So then it took Albert Einstein to figure out how does this work, and he said that, well, the gravity, it's not really a force, but it's actually the geometrical thing, right? And what he said is that for gravity, the source of gravity is the space-time itself. Now I use the word space-time. So which means that we have space and time is combined, right? So and now this might appear at first as weird, right? What is space-time? But if I give you an example, consider you call a friend and you say that you want to meet that friend at some place. So let's say this is your destination, right? You want to meet them at let's call it X. So you want to meet them at X, and you call them and you tell them that you decide that let's meet at destination X. Well, that's well and good. But what is the other piece of information that you have to give them to successfully meet at this destination X? So you have defined your space to them that you want to meet at destination X, but you need another piece of information to give them so that you can successfully meet at X. What's that? Well, that's time, right? So you have to let them know the space, which is this destination X, and at the same time, you have to tell them the time when you want to meet at this destination X. So you have to specify these two coordinates, X and T, to meet successfully at this destination X. So if you think about it, space and time have always been connected. So it's not something new. But you think about it for the first time, and it appears as though it's something very different, but it's not, right? So, but we'll not be focusing on the geometrical theory of gravity. We would be more concerned with the Newtonian's idea of gravity in this case, in this chapter for our NET. So the universal law of gravitation was given by Newton, and it reads, the force of gravity is equal to m over r squared, and there is this constant g. This constant is a Newtonian constant, right? And this capital M, it's the mass of the source of gravity. So for example, if you consider a sun-earth system, then the source of gravity is main source of gravity is due to the sun, because the earth is in orbit of the sun, right? So the capital M is the source mass, which is the mass of the sun in this case, and small m is the test mass, which is orbiting the sun. We call it a test mass, and so that's the mass of the earth in this case. And r squared is actually the distance from the center of the sun to the center of the earth. That's r, right? And as you can see that the force varies inversely to r squared. This thing is also known as inverse squared law. So this thing is termed as inverse squared law. Now, this means that if the radius between the two bodies would increase 2 times, that would decrease the force 4 times, right? Now, the reason for this negative sign comes from the fact that this r vector, so for example, if I have two bodies, then the r vector is pointing radially outwards, right, between the two bodies. However, the force of gravity is basically pointing inwards. So this is your vector r, and this is your force of gravity, which is pointing inwards because it's an attractive force. Hence, to include for this thing, we have to have this negative sign in our expression. So hopefully that makes things very clear. Now we can define something which is the acceleration produced due to the force of gravity, and that's defined as this thing, where g is the acceleration of gravity and it's equal to minus gm by r squared, and this negative sign is again due to the fact that we just explained over here, right? So the radius is pointing outwards, and the acceleration of gravity would be in the direction of the force, of course, and which would be pointing inwards. Now you can write this thing down as in terms of the density of the earth, or density of the planet, or any mass of the object as well. So how do you do that? Well, we know that density is defined as mass per unit volume, right? Now we can assume our planet, or the mass, to be almost spherical, and hence the volume of a sphere is given by 4 by 3 pi r cubed. So this means that I can write down my acceleration of gravity as this expression over here, 4 by 3 pi rho g times r. So if I were to put the value of this density over here with this volume in this expression, it would essentially basically reduce to this expression over here. So we have this one, acceleration due to gravity, in terms of the density of the mass or this object, right? Now note over here that this acceleration of gravity, it depends on r, right? And hence, so this should mean that if you leave the surface of the earth, so for example, here is earth, and you jump, right? So you jump, or you can even this is one example, right? So you jump, so the radius of the earth was this r, but now the force of gravity that would be affecting would be actually this r plus some height that you jumped over here. Another thing that you could think of is you are on the earth, on the earth, and you suppose that you want to see what would be the gravity at this point on the earth, right? Or you could also think about this, that this is the earth, and on the south, on the north pole, for example, the gravity of the earth would be something else compared to the gravity of the earth on the south pole, and the gravity on, let's say, the equator of the earth. So let's discuss this case in detail further, as the variation in the acceleration due to gravity. So here we have, this was the expression that we originally had, right? So for now we can just drop off the negative sign and we can put it back in later on. So, but to discuss the variation in g, we don't really need that negative sign at the moment. So, well, we have this expression we had in general. Now suppose if I jump, or if I want to see the effects of gravity at some height h, which is above the surface of the earth, which is this height, so we would just add that height in the radius of the earth, right? And so we would have this expression for acceleration due to gravity. Now you can say that we should differentiate this g from this one by just putting a prime symbol on top of it. And now what I can do is I can find a relation between these two g's as this, right? And now if I were to define some vector r as the sum of this radius r plus h, then I can write down this expression even more compactly as this thing over here. So the acceleration due to gravity at some height h above the surface of the earth is equal to the acceleration of gravity at the height at the surface of the earth times this radius of the earth over the total vector, which is the radius of the earth plus that height, which is capital R. Now suppose that if your height h, it is negligible compared with the radius of the planet or the mass, then you have the acceleration due to gravity, the new acceleration at some height h, would be equal to g times 1 minus 2h over r. And you can work this out by playing around with this expression over here. We also have a case where the value of g would vary with the depth, right? And that's just defined as g prime is equal to g times 1 minus d over r, where d is the depth, right? And so this means that as we go below the surface of the earth, the value of g would decrease, right? So the new value would be smaller compared to this value of g, as we have 1 minus d over r in this bracket. So this thing would be less than 1. The variation in g could also be due to the shape of the earth. Now earth is, well, a more realistic approach to the shape of the earth is that earth is actually elliptical in shape, and it's flattened at the poles, right? It's flattened at these poles. So this is the radius to the pole, and this is the gravity due to the at the pole. And you can see that it's bulged out at the equator, right? So here we have that the radius of the equator, it's about 21 kilometers longer than the radius of the poles, right? So at equator, the acceleration due to gravity is defined as gm over the radius of equator squared, and at the poles, the acceleration due to gravity is defined as the gm over radius at pole squared. Now you can do one thing, that you combine these two, and then we can, by combining these two, we can find a relation of the acceleration due to gravity at poles in terms of the acceleration due to gravity at equator. So upon doing so, which means that you would have to put the radius of the equator, but we know that the radius of the equator is definitely larger than the radius of the pole by looking at this elliptical shape of the earth, which would mean that the acceleration due to gravity at the pole should be larger than the acceleration due to gravity at the equator. So think about it in terms of this expression over here, right? So that makes sense. Now, if I put in these values, this would give me the acceleration due to gravity at poles is equal to acceleration due to gravity at the equator plus some value, which is 0.018 meters per second. And hence, the weight of the body will increase as it's taken from equator to the pole.